Hello, everyone, and welcome to the One World Combinatorics on Words seminar. We are very pleased to have here today Julien Cassaigne from Lumini, and he's going to speak to us about the Heinis spectrum.
Okay, thank you, Jeff, for the introduction. My talk is about the Heinis spectrum. I will tell you in a moment what it is, but I have to introduce it slowly. Then we'll see what we can do with this spectrum. There will be a lot of questions. If I have time, I will say something about rosy graphs and other tools to compute things. I will see. So this is about complexity of infinite words. So no big surprise if you have already listened to my talks. So here I will deal with one-way infinite word on some finite alphabet A, but this can be adapted to similar contexts like subshifts and so on. And so when you have an infinite word, you can take its factors, which are the finite words that occur in it, and they make a nice language. And then you can count them according to their length. And then you get the complexity function. So it maps any integer, positive, non-negative integer n to the number of distinct factors of length n that occur somewhere in the infinite world. And there are many interesting questions you can ask on complexity. So here I've attempted a classification of different kind of questions that can be found in the literature or in research programs. So the first thing you can do is you take your favorite infinite word and you say, okay, what is its complexity function? So compute. And then you can generalize a little and take a family of infinite words that is defined by some property, whatever property, so maybe coming from some kind of dynamical system or having some particular combinatorial definition, like using substitutions and things like that. And then when you restrict to this family of words, what are the complexity functions that you obtain? So the complexity function grows not more than this, or it is in particular class of functions. Third kind of problem is the reverse way. You fix a class of functions, or just a single function, and you want to describe the infinite word that produce this function as a complexity function, or that produce a function in this class as a complexity function. If it exists, make an explicit construction. So let's say I take P of n equals 2n plus 5, construct me a word that has complexity 2n plus 5 for n large enough. And finally, you may want to tell more and describe all the words that have a given complexity function or complexity function in a given class. So here, the typical example is if complexity function is bounded, then your word is eventually periodic. And eventually periodic have a bounded complexity function, so you have a perfect equivalence between the property of the word and the property of the function. Another famous example is Sturman words. Complexity n plus 1 is equivalent to 100 different properties of Sturman words. And there are not many more examples of theorem of this kind. So here in the present talk, we are interested in type 3 question. Maybe I should move this away. So if I restrict to, complexity with linear growth, what are the complexity functions for which there exists a word with such a complexity? So what are the different linear growths of a complexity function? So there are lots of examples of words that have linear growth complexity function. This is a bit surprising because if you take a random word, it has exponential complexity function. Random word in the sense that you flip a coin to get each letter of the word, then almost surely you will see all the possible factors in it. So complexity function will be 2 to the n if the alphabet is binary. But in practice, you're interested not in random words, but in interesting words. And it happens that many interesting words have linear complexity. And here I've listed a number of them, of classes. So words generated by finite automata, automatic sequences, words generated by primitive substitutions, Sturman words for any, so that you can define like encoding a straight line, so for any slope, and then generalization, various generalization of Sturman words like episturmian or Arnoux-Rosy words. You get complexity 2n+1 for Arnoux-Rosy and k-1 n+1 for episturmian on the k-letter alphabet. Coding of certain dynamical systems like interval exchange transformation. You get also k-1 n+1. A whole class of interesting words that are called dendric words. Then you do not necessarily have this +1 at the end. So other linear function like 2n outer words, paper folding words. They have 4n, but you need to take n large enough. Of course, if you have a function like 2n, it cannot be for all n because p of 0 is 1. So you have to start from some value, initial value. So many examples with exact linear function, a n plus b after some point. But most of the time, and for instance, if you look at substitutive words, most of the time, what you have is a linear growth, but not with exactly equal to a linear function. So more typical is the case of the two-Morse word. So two-Morse word, I think most of you know what it is. It's a fixed point of a substitution, binary, constant length too, so it's also an automatic sequence. So there's at least two reasons in the previous list for which it has linear growth complexity. And the exact complexity function was computed by Schrecz-Koblak in 1989. And it's not as simple a formula as the previous ones. You need to make cases. And so the complexity is 4n plus constant in some intervals and 2n plus constants in other intervals. And the intervals, they change at powers of 2 and 3 times the power of 2. And the constants, they are adjusted so that the function is continuous in the sense that at the point at the boundary between two intervals, both formula give the same value. And so this is typical for substitutive words. And so it is not, it is, of course, big O of n, but it's not equivalent to some constant times n. If you divide by n, you get something that oscillates between two values, and in this case, it's between 3 and 10 over 3. So this is, yeah, as I said, this is the typical behavior, and the intervals on which a given function applies, so like 4n plus constant, they are longer and longer. usually. And the points where you change from one to the other, they follow some sequence that grows exponentially. And that can be described using by special factors. I will speak about this at the end. So now I'm ready to introduce the Heinis spectrum. So this, as I said, this function may have, P of n may have linear growth without being equivalent to constant times n. And so it's interesting to look at the ratio P of n over n and see between which values it oscillates. So let's define alpha as the limit inferior of P of n over n and beta as the limit superior. And so P of n is equivalent to constant time n's if and only if alpha equals beta. And in his PhD thesis, Alex Heinis, who was in Leiden for his PhD, proved that beta minus alpha cannot be 0 when alpha is between 1 and 2. And it's more precise than this. There is an explicit lower bound on beta minus alpha that depends on alpha, and that is 0 only for 1 and 2. So it is impossible to have complexity equivalent to alpha n for some alpha which is between 1 and 2 strictly. And with François Nicolas, we extended this result to any real number which is not an integer cannot be the limit of P of n over n. So really, most of the time, what we will have is point alpha beta with different values alpha and beta. And so we introduced the Heinis spectrum as the set of all the possible pairs alpha and beta that you can obtain from the complexity function of any infinite word on some finite alphabet. So they may be infinite in the case when the growth is not linear. They can be 0 in the case when the complexity is bounded. The size of the alphabet is not specified, but actually it's not difficult to see that a binary alphabet will give the full spectrum already, because it's always possible to encode any alphabet in the binary alphabet in a way that will not preserve complexity, but change complexity without changing the values of alpha and beta. And so the general question is, what can be said about this strange set omega? So here are some points that fall in the spectrum. So periodic words, bounded complexity gives 0, 0. Sturmian words, complexity n plus 1, you get 1, 1. And more generally, all the words with complexity kn plus constant give the point k, so the integer points on the diagonal. And then two more, we have seen 3 and 10 over 3. If you have exponential growth, like the Champernon sequence, you get infinity, infinity. But there are more complicated values that are not too difficult to construct. It's, for instance, you can construct a word with 1 infinity. So the complexity at some point is almost n. Of course, n plus little o of n, which will not be bounded. And for other values of n, it will be larger than any constant times n, and so you get 0.1 infinity. The second one corresponds to the period doubling word, where you get 3/2 and 5/3, which is exactly half what you get for the two-Morse word. And, well, this is not surprising because there is a simple relation between the two. But you can also get other points. And the third one, I forgot how it is obtained, but that's for some substitution. That's what you will usually get for a substitutive word with two values that are obtained. So to compute those values for fixed point of a substitution, you will have to compute the length of the bisexual factor, which will amount to compute the length of iterates of the substitution, which will amount to compute the powers of a particular matrix. And so you will get algebraic numbers that involve the eigenvalues of the matrix. So this kind of number. Okay, and so I have plotted many more examples, and you get something like this. So here, all the red dots, they correspond to particular substitutive words. The graph is restricted to the part between 1 and 2, which is the part that was studied by Alex. And it's actually the lower part of the graph if you exclude the 0.00 for periodic words. And then, so the green line is the obvious bound that alpha is less than beta. So alpha is horizontal, beta vertical. Alpha is less than the limit, inf is less than the limit sup. The blue curve is the bound proved by Alex Heinis. So low bound on the difference, that is 0 on one and 0 when alpha is 2, and non-zero in between. And you see that there is a red dot on the blue line. This is the paired doubling word, so 3/2 and 5/3, which falls exactly on the line by Alex Heinis. And it is the only, I mean, apart from the both ends, 1 and 2, it's the only point that is in the spectrum on the line. The rest of the line is not in the spectrum. So I will explain the purple line later. So with this picture, we see that the structure does not seem simple. There are some areas that seem to be denser than others, but of course this may be an artifact due to the choice of points for this graph. There are parts that are completely white, so maybe it's empty, this part. There are some sequences that are visible. For instance, if you look at the lower part, you will see some points that follow a parabola, and it's exactly a parabola, actually. And, well, part of a parabola. And they will accumulate to 1, 1. This is not visible here. It stops quite far from 1, 1. But if you continue, it will go closer and closer. And these points, they were computed by Ali Aberkan in one of his papers. Okay, so here is another graph with more points. So you see that the white part that was close to the vertical axis is getting filled. But the white part that was close to the blue line is still there. So there really seems to be an empty part and some isolated points, and maybe some part where the points are dense. So interesting structure. Okay, so let's start with isolated points. Of course, 0, 0 is isolated, but it's not very interesting. So I'm really interested in isolated points in this subset of the spectrum. And so here there's a result by Ramzi Turki from 2016 that the point corresponding to the paired doubling word is isolated. So it is, so this is the paired doubling word, yes. And the term says that if beta is below a certain line, then alpha beta has to be this point. And the line is the purple line here, which is slightly above the blue line. So it means that there is nothing else than this particular point, and so the point is isolated. And the bound is given as a minimum because there are several conditions, excuse me, that there are several conditions that must be fulfilled to prove that the point is necessarily this one. And I will give some of the tools to compute this. It's rather a long computation to obtain these formulas, so I will not explain in detail, but I can give some tools. Okay, so we have found one isolated point. There is also accumulation points. Well, I already mentioned this result. If you look at this family of substitutions, so A maps to AB and B maps to AB repeated a large number of times, AA. And then you can compute exactly the values of alpha and beta. They're algebraic numbers, as I said. And they behave when L, so the number of repetitions of AB in the image of B, when L tends to infinity, they all tend to 1. But they don't tend to 1 at the same speed. And so they follow some kind of parabola. So alpha minus 1 is about the square of beta minus 1. And so they accumulate to the point 1, 1. Okay, so these are two examples of things you can do. Here are many other questions about this set. So construct points. So I've, of course, the figure there are computed with from particular families of substitutions, but there are other families for which we can compute values of alpha and beta, so get points of omega. And so Katie Lloyd has a paper that is called, I think, More Points in the Heinis Spectrum, where she constructs families like this. Then points with particular properties, like isolated points. So we have proof for one point. It seems that there are many others. And so Firas Ben-Ramdam is currently working on this, trying to generalize the methods by Ramzi Turki to adapt them to other points than the doubling sequence, to prove that there are infinitely many, or well, at least other isolated points in omega. Then, is there some interior? So can you find some area where all the points in some little square are in omega? Maybe something which is more reachable is, does it come close to any point in the, sorry, can you reach in omega any point in the vertical axis? So you want to have alpha equal 1 and any specified value of beta. And this is probably not too difficult to construct this using, for instance, some S-adic construction. It will not be a fixed point of a substitution to get this. Then you can study subsets of omega where you restrict word with a given property. So here I mentioned the criteria of Bocher-Nitzan on unique ergodicity. So I recall them. If you take a subshift for which alpha is less than 2 or beta is less than 3, then it has a unique ergodic measure. And so if you have a non-uniquely ergodic system, it is some above 2, 3, above this point, above and right. But of course, it does not mean that all the points in omega that are above 2, 3 are reachable with this kind of examples. So what can you get precisely? Maybe a simpler question of this kind is what do you get if you restrict to words that are uniformly recurrent, or minimal if you prefer. My belief is that this will not change omega, and all the points that you can obtain them with uniformly recurrent words, but I don't know how to prove this. And then the last two questions, they correspond to properties of omega when you take limits of points that are in omega, and they would be nice to give a better meaning to the pictures that I've made. For the moment, the picture, they're just dots corresponding to examples. And so they prove nothing. But these points, they are obtained by purely substitutive words, a fixed point of one substitution. And it's not too difficult to compute the values of alpha beta for such points and to describe family of them, and actually to compute all of them. Of course, there are infinitely many, but all of them up to a certain length or something. So you can feel a part of omega just by substitutive words. If this is dense in omega, it means that the picture that you draw visually is omega. You can get as close as you want to any point in omega. So this seems rather natural, but I'm not sure how to prove this. Okay, is omega compact? So of course I've added infinity, otherwise it's certainly not compact if you can go to infinity, but here, is it compact? So if you take a limit of points corresponding to infinite word, what you get, is it a point alpha beta corresponding to another infinite word or not, etc. So many questions, mostly open on omega. So now, what time is it? About half time. Yes. So I will say a word about the tools that can be used to study the Heinis spectrum and to compute those values. And so tools for describing the complexity function of infinite words. And one of the main tools is the use of Rosy graphs. So what is a Rosy graph? It's a directed graph that represents the factors of length n and n plus 1, where the factors of length n are exactly the vertices, and you put an edge between two vertices when, so x and y, when there is a factor of length n plus 1 that starts with x and ends with y. Here okay, I said the edges correspond to factors of length n+1, but actually it's more interesting to label the edges with a single letter. So take the first letter of Z. The reason for that is when you make path in the graph, then you just concatenate the letters that you read on the edges. So for instance, if you take the Fibonacci word, so it has complexity n+1, and so you get graphs with n+1 vertices and n+2 edges that look like this. So you see the shapes. Okay. Well, you can recognize different things in them. There are vertices where the graph branches, so you have two different outgoing edges, and there is exactly one in each graph. This is particular to Sturman word. I will come back later. And the rosy graphs, you can view them, if you like, as automata that approximate the language of you. So so to view them as automata, there is no initial and final state, so you can start anywhere, stop anywhere, and you just read what you see on the edges. And so you get the language that is larger, but that describes exactly the factors of the infinite field up to length n+1. And so if you make the intersection of all of them, you get your language. And so I mentioned vertices with several outgoing edges. This is exactly equivalent to right special factors. So right special factor is a factor that has several possible extensions to the right. So W is a right special factor if there are two letters A and B, such that WA and WB are both words in the language with A different from B. And a right spatial factor is exactly a vertex with two outgoing edges. You can do the same to the left with incoming edges. And the number of right spatial factors, so for general alphabet, you have to count them with multiplicity according to the number of outgoing edges. For the binary alphabet, the formulas are simpler because you have one or two outgoing edges, so exactly two when it's special. And then the number of right special, it's easily seen to be P of n+1 minus P of n. So if you take any factor of length n, it occurs somewhere in the infinite word, so there is at least one way to extend it. And so you can associate to it one factor of length n+1. But when it's special, then there is another factor of length n+1 that also starts with it. So it increases the number of factors by one each time you have a right special factor. So the number of right special factor is the first order finite difference of the complexity function. For right special, for less special, it's the same except when the word is not recurrent, which I will not explain further. Okay, let's skip this trivial case of periodic words. So when you have a Sturman word like Fibonacci, complexity is n+1, so the number of special factors is exactly 1, which means that in the graph there is one left special factor and one right special factor. And well, you can try to do graphs that have these two factors. There are only two possibilities to do this and to have a graph which is strongly connected, which is another constraint for Sturman words because they are recurrent. So you can go from anywhere to anywhere in the graph. So this excludes a graph where you would have one loop and then some path that goes to another loop, but no way to come back to the first loop. And so there are only two possible shapes that are here. So in these drawings, I've not represented the vertices that have exactly one incoming and one outgoing edge. And that's what I call the shape of the graph. You forget this information and you just look at branching points. And so the two cases are when the special factors are different or when they are the same. Okay, so two possible shapes. And now we'll see what happens when you change the value of n. So you look at rosy graphs, not at a particular graph, but the family of graphs. And a graph in the family and the next graph, they are closely related. Usually when you have Gn, you can almost predict what Gn plus 1 will be. This is not particular to Sturm words for any case. And more precisely, if there is no bispecial factor, bispecial means both left and right special, then you can completely predict. If there is a bispecial factor, then something may happen. So if there is no bispecial factor, let's look at G4 and G5 in Fibonacci. Yeah, it's really mechanical to go from one to the other. Any edge in G4 becomes a vertex in G5. And you connect them if the two edges were connected in G4. So I say 4 and 5, but that's n and n plus 1. So for instance, here you have, if you look at the top left of the graph, you have BAABA, which corresponds to the edge that goes from BAAB to AABA. And after this one, after AABA, you see that there are two outgoing edges. So from BAABA, there will be two outgoing edges that go to the two words that you can obtain that way. And so in this graph, you see that the loops that you get are the same in the sense that they have the same length that the loop that you had in the first one. So here you have a loop of length 3 and a loop of length 5 in G4 and same in G5. And the only thing that changes is the common part between the two loops. In G4, the two loops, they have a common part of length 2, and in G5, they have a common part of length 1. And what will happen is that the length of this common part, it will decrease by 1 each time you increase n. And so at some point, it will become 0, which means that this common part will shrink to a single vertex, which will be bispecial. And so we will come to the second case, when you have a bispecial factor and you go to Gn plus 1, then this bispecial factor is replaced by a certain number of edges. So in the binary case, at most 4, but some of them may not exist. And so there's a choice. Of course, for a given word, there's only a single Gn plus 1, but you may have two different words that have the same Gn and two different Gn plus 1. So in the case of Sturm words, you have when you have bispecial factors, you have two loops that are usually called X and Y. And the bispecial factor bursts, you have edges that goes from the right part to the left part or the other way around. You cannot remove them because otherwise the graph will not be strongly connected. But the two vertical edges, you may remove them, and actually you have to remove one of them exactly to get the right complexity. And so you have two choices. And these two choices, they can be summarized in this graph of graphs. So how to read this? You start from the top, you have this rosy graph with two loops. And then in one step, so one step means increase n by 1, you have two different ways to go to the next graph by keeping one or the other of the vertical edges. And then let's say the left branch, so you have this graph, you see there is a loop on the left, which has length x, and a common part between the two loops that has length of x minus 1. And so for a time, so again, time is n, a time of length of x minus 1, nothing will happen except that this common part will shrink. And after x minus 1, you get a graph, which is, again, a graph with two loops. And now the small loop is the loop x, and the big loop is the one that's obtained by going through x and y. On the right side, you do the same, but with the reverse choice of loops. So y is conserved, and there's a new loop, which is yx. And so you see that when you do this, you obtain a graph that is of the same type as the one you started with. So that's the dotted lines that go back to the top, but with different loop labels. And the loop labels are obtained by some simple transformation from the initial ones. And then you repeat, and you have a choice, each time a choice, and the choice is given by the directive sequence of the Sturman word. Or if you, for instance, if you view this as a continued fraction, additive continued fraction of a slope, then you will have also two cases on the continued fraction, whether the left or right number is larger, that will decide on which side you go. So this is related to the arithmetic properties of the slope of the Sturman word. So any path, any infinite path in this graph will produce a particular Sturman word, except a path that goes only on the right part. If you loop only in the right part, then the small loop with y will never disappear, and this is not possible for a Sturman word. Okay, so that's Sturman word. For the Heinis spectrum, you get only the 0.11 if you do this. But now let's, okay, maybe I will, so you can express the values of x and y at each point. Okay, I will come back to this. Now let's to get points in the spectrum that are above the 0.11. And the main idea, the starting idea is that if the complexity is not too big, then P of n plus 1 minus P of n will be 1 infinitely often. And when it is 1, then the shapes of the graph that you will get are the same as the one that you get for Sturman words. So we can start with what we have for Sturman word and modify it a little. And so this is the case in particular if alpha is strictly less than 2. And so if you are in this situation, I will come back to the substitution, what you have is that we start with your graph with two loops. You have the left branch and the right branch that are exactly what you have for the Sturman words, but there's a third possibility, which is that you may keep both vertical edges. And the result of this is that the P of n plus 1 minus P of n, the first difference of the complexity, will become 2. So the growth of the complexity will be slightly faster than for Sturman words. And it will be 2 for a certain time, and until one of the special factors disappears. And so you can adjust, if you can adjust the time for which the difference of the complexity is 2, then maybe you can adjust the value of beta. So I'm vague at this point. So what will happen next is that the shorter loop will eventually go around once, and you get the bispecial factor. And then you burst this bispecial factor again. So it's in the middle here, and there are 4 different ways to burst it. But some of them, they will increase the complexity again. So the one to the bottom and the one to the left, if you continue them, the complexity will grow, and you will get a value of beta that is larger than some bound. So we don't want this. And only the other 2 we keep. so I'm back to the, sorry, starting from the H-shaped graph. So if you go to in the middle, you do this thing, and at some point you get the bottom graph, and then you have two choices, and one choice amounts to going back to the graph above, and the other choice goes to a graph of the same type as the one to the left. And so one theorem from Alia Berkan is that if the complexity is not too far from n, so typically if beta is less than 4/3, then the graphs are of this kind. They are somewhere in this diagram. And so your infinite word is corresponds to some path in this diagram. And you see that this path, you can describe it by a family of operations that always come back to the top rosy graph. So you can either go to the left and back, or go to the right and back, or go down, do a certain number of time back and forth between the second and third graphs in the middle column, and at some point come back through the left part. So we have a family of what we call evolutions of graphs. Now the job is to link the sequence of evolutions with the values of alpha and beta. And intuitively, the evolution that involves going back and forth in the middle will increase beta, and the two evolutions that correspond to Sturman words, they will lower alpha. Okay, and that's something else. So maybe I go back and I say something about aesthetic. Another way to interpret these evolutions is to use substitutions. So if you look at the labels of the loops, then we saw that the loops after something are obtained by simple formulas like xy, yx, starting from the labels of the loop at the previous step. And so if you so we can construct substitution tau I, so that tau I of A is the label of the left loop, of the big loop, and tau I of B is the label of the small loop at step I. And so at the next step, what I call step is each time you come back to the 8 shape, or infinity shape rosy graph. What you get at the next step is a combination of what you had at the previous step, and this amounts to composing the substitution tau I with one of these oops, what's this? Sorry. Sorry. So composing with one of these substitutions, phi or psi. That's in the case of Sturman word. Phi corresponds to the left path, and psi to the right one. And then if you are in the more general case of low complexity, you have additional substitution phi m that correspond to the left part with m minus 1 times going back and forth between the two bottom graphs. And so we have an infinite family of substitution, and we can make an aesthetic construction with those substitutions, so composing them in any order to construct the infinite word. So as soon as you use infinity often phi m with m at least 2, then you will get something which is not Sturman. And as a remark, these substitutions are almost the same as a substitution called tau m plus q plus 1 and q plus 1, introduced by Kreutz and Pavlov in a paper where they construct this, but then they prove other properties related to measures on this infinite world. And so this is how I constructed the graphs at the beginning, by taking enumerating sequences of substitutions phi m or psi. So I take a finite sequence of length 1, 2, 3 up to some point of those substitution. I compose them and I take the fixed point of this. Okay, and there's one last result I wanted to mention, which is not exactly in the. So this is one. All of this is in one point in the Heinis spectrum. It is possible to characterize exactly the words that will give the point 1, 1 in the spectrum. So if you are at point 1, 1, of course you have low complexity in the sense I defined. So you know that your infinite world is obtained by the evolution that we described. And so we have some composition of phi m, phi mj for a certain sequence of mj, and psi repeated the number qj. So any composition of phi m and psi can be expressed in this way, where you alternate doing phi m j for some mj and doing qj times psi, and you repeat this. And so the theorem by Ali Aberkan is that the complexity is n plus little o of n, which means exactly alpha equals 1, beta equals 1, if and only if the language of U is the language of the S-adic sequence obtained with such a sequence of substitutions, where the numbers qj and mj satisfy this infinite limit. So the qj have to be large enough, and the mj have to be not too large compared to the qj. So there is a trade-off between q and m. Well, this is what I said at some point, that if you do the Sturman evolutions, that's the psi, then you will reduce alpha, and if you do the non-Sturman evolution, so the phi m, then you will increase beta, and so they move in opposite ways. And if you do psi a big number of times, then you will reduce everything. And if this qj grows faster than mj, in the end, the limit will be 1. Okay, so I think I will stop here for the talk. I did not have much time to explain how precisely you prove that, for instance, the point is isolated. How do you prove that something is not possible in the Heinis spectrum? Okay, it's a bit too technical. So thank you.
Well, thank you very much, Julien. Does anyone have any questions?
Question in the chat.
Yes.
I did not that. Yes, it's here.
Here, I'll read it out for everyone. What is the cardinality of omega? Is it uncountable? If it's not uncountable, then some of the topological questions would be answered.
Yes, so that's of course a very good question to add to the list. So obviously omega is infinite. Is it uncountable? Probably yes. So for instance, one of the question was, is it true that all the points in the vertical axis are in omega? So if this is true, then it's uncountable. Now, is there a simpler argument to prove that it is uncountable? Maybe. So the points that I can construct correspond to S-adic words that are defined by a sequence of psi and phi n. And of course, there are uncountably many of the choices of an infinite sequence of substitutions. But of course, you then have to prove that they give different points. And this is not completely true. Like all Sturman words, they are uncountably many of them, but they all give the same point. But maybe it's possible to find a subset that is still uncountable and for which you can prove that all points are different. Maybe. That does not seem immediate. Okay, anyway, my guess is that it's uncountable.
Let's see. Dan asks in the chat, are the substitution points dense in the strip 1 times the interval 1 to 2?
1? Sorry. What's the strip?
Just alpha equals 1 and beta is the interval from 1 to 2.
Okay, just the line. Alpha equals 1 and 1, 2. Okay. Well, there are no substitution points except 1, 1. For you see in the first, you still have the yes. If you do substitutions, so these are substitutions up to a certain length, you see that there is no point except 1, 1 that falls on the vertical axis. So substitution, they get closer and closer to the axis, but you don't get anything exactly on it.
Is there some obvious reason for that? Like basically you're saying substitutions have to fluctuate.
Yes, they have to fluctuate. Okay, substitutions, it means that the path that you do in the graph of graphs is periodic. The S-adic presentation is periodic. So the result on the graph of the complexity function is that you will have some pattern. Let's say in the case of tumors, it goes by slope 4 for some time, then slope 2. So some pattern like this that will repeat at larger and larger scale. And so you will have long intervals on which P of n plus 1 minus P of n is constant. And it's constant as 1. It's constant and it's an integer. And so if this integer is 1, if this integer is 1 all the time, then you get 1, 1. If this integer is at least 2, and you look at the point at the end of this interval, then here the complexity will be more than a constant larger than 1 times n. Because you have spent a positive proportion of your time with slope at least 2.
Right. But I guess if you allow yourself an H-dole, so you apply a morphism at the end, you can eliminate this fluctuation.
Yes.
Right?
If you do H-dole, yeah, but then you will not be able to grow beta. I mean, if you eliminate it, you will eliminate it completely.
Right.
H-doll do not change anything in the points that you obtain, because well, that's not completely true. They may, of course, the complexity may collapse. Yeah. Now, I think you can get rid of H-doll and prove that H-doll and C-doll and so on, they all produce the same points in the spectrum as just purely substitutive.
Okay. Oh, Dana has another question in the chat. Is it known how alpha beta changes under a factor map? Do they both decrease, or can just one of them decrease while the other remains?
I don't know. Decrease. It does not seem easy to have one decrease and not the other one. Yeah, this seems difficult because I mean, if one remains, that it means that for a certain subsequence of lengths, the factor map does not reduce much the complexity function. But if this is the case, it probably cannot reduce it much for the other values. Okay, that's okay. Of course, it's possible to construct examples where it behaves like this. If you take so not substitutions, but more complicated words that get alpha equals 1. Because then alpha equals 1 and some big beta, and then you can make a factor map that decreases beta, but alpha cannot decrease below 1, so it will not change. The other way around, so with a beta that does not decrease and alpha that decreases, I don't see how to do this.
All right. Are there any other questions for Julien? If not, yeah. Thanks very much, Julien, for your talk.